I still can't tell what type it is.
Nobody.
Steve Jobs went to after Apple.
Oh, next up. My heart.
Wait, but what operating system is that?
Solaris.
Solaris.
Oh, Slayer.
Oh. Oh yeah, that was good. I don't think anyone when I was ever tried with this.
Nobody here has ever heard of Solaris.
I've heard of it.
One.
Heard of it.
One overachiever. Two overachievers. Three overachievers.
It's like a light day. It wasn't even like a hard.
You raise your hand at all the right times, so I think you know.
like two things, and I was like, no, I can't walk.
Solaris is from 1972.
2 days.
No, not that one. No. That's a SunSpark 5.
It's also a Sun computer. Spark architecture.
Oh, that's a.
With like Java like code. No, it's just like some programming languages and compilers.
There's a 2002 movie called Solaris.
Oh, it's lavender. Oh. Yeah, that's like a. When you said purple, I was like, deep. I'm like lavender.
Maybe a little lighter.
A lot lighter. A lot grayer.
That has been sitting under like.
Sure. What's the name of the IBM Food Spring? Oh yeah, sure. You've been I know it.
One of my
I can like the Model M. Yeah.
Yeah, that's what I'm looking at right now.
They're like it's Model M. Yeah, Model M.
Yeah,
I own the original.
It sounds like a diesel engine that's old, which is amazing.
You think I can get this? I have an old Delphi key with like the little adapter thing, and I like it, but I need a cooler one.
No, there's nothing cool.
The Model M's are cool, but like it was not worth it. It gave me because I used to play World of Warcraft. I was like mashing like 500 times a second. And
You gotta like work these muscles out to get rid of them.
yeah. I'm
It's actually recording.
Oh yeah.
Oh wait, what?
We gotta lock in this recording.
Oh yeah.
Okay. Sorry.
All right. New procrastinators who weren't here a second ago. Homework due. 11:59 tonight.
Just any time before.
Hopefully now you will realize that homework is supposed to be 3 hours a week, right? 3 hours a week? Yeah. Working on homework, so that's like 12 solid hours of debugging to get those problems right for a lot of people. So if you do start the day before, it's going to be 12 solid hours.
Or you do 12 solid hours the night of the science.
And then you're done.
I like the calm response there.
I like it.
Yeah.
That's when's the next lab? It was supposed to be today, but it will be
11th, right?
rock lab, and it will be. I think it might be immediately after spring break, actually. Yeah.
So the labs don't like
Not completely. The first one did because we had to walk through kind of the basic thing before we started. Before we gave the homework.
You said lab 3 is about 2 homework 1 explanation.
Yeah, okay, so.
It's the 11th, right? Next week.
Yes, on the 11th. Let me start this recording. Yeah, okay, so on the 11th, I will give out the midterm. It's going to be a 48-hour midterm for people without accommodations, which means that on the 13th, we will be in a class, which is when the official midterm takes place, and anyone who has questions can come and sit in that class, and it's doing in that class, and we will help you with the midterm, okay? But the other thing that we're going to do on the 11th, apart from kind of intro to midterm and hand it out, is go over the homework responses. I had wanted to do that today, but anyone with accommodation, it is due Friday at 11:59, so I can't do it today. We'll do it next week. But today, we're going to talk about another thing that's going on, which is your final projects. There we go. Your final projects, Jade has pass out something or other that you got to fill out by Friday. If you haven't selected a final project, I want to talk about some things that would be good final projects. And then we're going to talk about using fuzzers for bug hunting and kind of the process around using fuzzers and how to think about them and how to build your own and how to use ones that already exist and what they do and why they do it, etc. But first, let's talk about some final project suggestions. I'm going to remove that create a homework style challenge. That one I'm not going to allow, but the rest of them on there we're going to do. So the first one, and kind of the highest difficulty that you're going to see, is probably finding an O-Day. Now, if you are going after one of the other final projects, you may stumble into one. And should you stumble into one, you're basically guaranteed an A in class. Okay? So if you structure your work on the other ones, such that you might find one of these, that would be good for you. So what is an O-Day? An O-Day comes from FTP servers. If you upload something to an FTP server, it's got a how long this has been on the FTP server time on it. And so if it says this file has been on the FTP server for 0 days, that means that somebody uploaded it today. And so the idea is that someone has uploaded a brand new exploit for a bug nobody knows about to an FTP server on their university's public FTP dump, and it says 0 days on it, and everybody has a field day walking around in the network. At least they used to back before you would get expelled from school for doing fun things. So how would I suggest that you do this? Always a combination of fuzzing and manual analysis, and we'll talk about kind of what that would look like a little bit later in class today. But say you do find something. Your project should then be an assessment of the exploitability of that bug you found. Is it or is it not exploitable? Why do you think so? Can you prove it? Can you write a proof of concept that exercises the bug? So a proof of concept is the smallest possible piece of code or the simplest possible piece of code that can exercise a condition in a program. Okay? So even if you are in your next step, we'll talk about in a second, and you are looking at an exploit that does exist, part of it's going to be reduce it to a proof of concept. That's going to mean proving you understand exactly what's going on in the program and writing this very, very small script that just makes that bug occur. And then the next step for a proof of concept would be getting it to the point where it controls EIP. Right? So you want one version that is as small as possible to make the program crash, and then the smallest possible thing that you can write to get control of EIP. And so both of those are proof of concepts of different things. So first one would be proof of concept that a bug exists. Here's how you exercise it. This is what you would give as a white hat to your software team. Say you are auditing software, it's your job to security test software. You find a bug, you will provide the very smallest reproduction case you can to those engineers so that they can test it to see if their fix works, right? And you want them to understand exactly what the problem is so they fix it correctly, which often they will not. Okay, so there's kind of two levels of proof of concept. You may be able to do this, and you may not be able to get to EIP. It may be too complicated for you to do that. That's still an A if it's likely exploitable. Okay. Not only is it an A, but you get to write it up. That means you get to write up a PDF of this thing. You will publish on probably your own blog or whatever you happen to have, and then possibly, if Larry allows us, a Cybersecurity Club blog. And then you get to put it on your resume, and you get to call MITRE and get an official CVE number for your bug, and you get the pleasure of disclosing it to a company, which is not pleasurable, but I'll walk you through it. But it means when you go to get your first job, you can say, found this bug in this program. Here's the thing you can look it up by. Here's all the documentation for when I went through this company, and that will be a huge feather in your cap when you go to do that, okay? And that's the full documentation, and I'll walk you through what that'll look like if you get to that stage. So that's option one. Option two, exploit a bug that already exists, okay? This one is going to be kind of a bread and butter final project. You go to Metasploit, You find something that doesn't look too hard from between 2007 and 2012. You set up the system in a virtual machine. You prove that the Metasploit exploit works. And then you take that thing apart and you write the proof of concept that's the smallest possible way to crash the program, the smallest possible way to get EIP, and then you write the whole exploit yourself and you document each piece. And you write the report, and the report says, I did this to solve this problem. I did this to solve this problem. The same way that we broke down EX1, except this will be more complicated. In this case, despite it being more complicated, you will have a perfect example of somebody else having solved the problem. And it will be your job to reverse engineer why they solved the problem in that way. And extra points if you can come up with a better way to solve it, or even if you can identify the problems with how they solved it. Right? There may be old exploits in Metasploit that rely on static addresses, and you could say, I would replace this static address with a jump to this code page, which is always at the same spot, and I can make this more reliable. You can make old heap exploits on Metasploit much more reliable if you make a bunch of allocations happen first. Right? There's some very simple ways to make these things more reliable. And if you select one of these things, I can help you with that, right? I will walk you through these processes for your final project. Now, it's possible you pick this, and when you start doing that, you start the fuzzing process that we'll talk about later on, and you will find another bug, right? That's also entirely possible, especially if you have selected an embedded device, which may or may not be more difficult in certain ways. This is basically the same. The question is sorry, I got that backwards, so let's pretend I talked about this. I'll go talk about this one. So an end day would be you have an exploit that's not, or sorry, a bug that's not been exploited. Stephen, I think, mentioned one in the Discord, which was the USB camera driver. Do you know what the name of it is? UBC, yeah. So if you pick that one up and you set up a Linux machine in QEMU and you write the exploit that works for that bug, that would be, basically just as good as writing an O-day, right? You haven't found a new bug, but you've written an exploit that did not exist previously, okay? All these essentially end up in the same place where you are documenting that process with those levels of POC and your understanding and why you made the choices you did, or why the author of the exploit made it. Last one, I think is probably a good candidate, is port what you know. So you could pick an architecture like ARM or an OS like Windows that we have not covered in this class. We've been doing 32-bit x86 Linux. You could do x64 Linux. You could do 32 or 64-bit Windows. You could do anything else you like. You could do OS 10. Do the homework examples on the new target. Some of those homework examples may or may not be exploitable on the new target. I may need to make changes. So if you select this option and you get stuck on any of them, come talk to us. I'll do the assessment and decide, okay, here's a new version that's similar, do that one. You'll do the examples and you will document the changes, how it affects exploitability. So even if it's not exploitable, I'm going to want to know what about the difference of the architecture, operating system, or compile options made it not exploitable in your opinion. And then you'll talk about what strategy you used on that new architecture. So this is a good one, especially if you have a job already that is going to focus in a certain area and you want to kind of get caught up on that. I will give you basically homework time to prepare for your new job or whatever job you want, right? And we'll guide you through that process. All right, so I mentioned Fuzzer several times in that discussion of how final projects might work. Does anybody have questions on final projects, stuff that they thought of that they might want to do that wasn't on that list? I know Stephen also mentioned updating a Fuzzer to find a bug that it doesn't currently find, which is an excellent process, so I would accept that as well. That would be another good final project. Has anyone select? Oh,
I
that's
said the final projects are in groups, right, for this?
Yep.
Okay.
Yep. It's groups between 1 and 5 persons. Yeah. And the more people you have, the larger your project will have to be. And if you have grad students, doubly so.
If we don't know what exactly we want our final project to be by Friday, are we able to just fill out the form and say, I don't know yet?
That's a thumbs up from the person who's really in charge.
Can we create like a server and then package?
Anyway.
Can you create a server and then package yourself? Or it's like,
No, so I am looking for XDev or reversing work, but not operations. So the act of breaking into something using tools you or someone else has written and putting them together and being evasive and exfiltrating data is operations, which is not covered in this class. That's the stuff that's actually illegal if you do it to something you don't own. It is always legal to reverse engineer for the sake of security. It is always legal to write exploits. It is legal to put out information in any way you want, however you like. No one can sue you, period. But if you break into somebody else's assets, that is illegal. That is the thing that is illegal. Now, I have seen friends of mine get busted for writing a tool and then handing it off to somebody who then performed an illegal operation with it, which is not illegal, but they did sell him down the river. And that should not have happened. But that's the closest I've seen, right? So here's the thing. If you write an ODE or you find a bug and you drop it on a blog publicly and someone uses it, now you're clear. But if you write it and you keep it in your pocket and someone else uses it, you're not clear, because now you are the only path to that operation. Does that make sense? If it's public, it could have been anybody. That is also a tactic that you could use to obfuscate what you are doing, and maybe some larger organizations do this, where you use a bug for several weeks and a couple operations, and then you immediately release it before anyone realizes that you have done those things, and now anybody on Earth could have done those things, right? So you burn your own bug to obfuscate what you're doing, but don't do that. Qualified people in governments. Okay, so fuzzers. Fuzzers are a way to find bugs, okay? I think the term was coined in like 1988, but it really didn't gain any sort of foothold in security circles until the late 90s, early 2000s. The first one that I became aware of that was kind of a big deal was Spike, and Dave Eitel wrote that one. And I think actually I talk about a bug I found with it later. But what you are doing is repeatedly creating a bunch of inputs for a program, and then you are going to inject them into the program somehow, and then you're going to see what happens. And you're going to do this over and over and over again as fast as you possibly can, generally just running it on your computer all night long while you're asleep. There are a number of ways that you can do each of these steps, and we're going to break it down. We're going to break it down for two reasons. One, if you want to write your own, which I highly recommend you do, because every fuzzer finds different bugs. It doesn't matter if you write the dumbest fuzzer in the world and somebody else has spent 10 years writing the smartest fuzzer in the world, your dumb fuzzer will find a bug their smart fuzzer will not find, period. And it mostly depends on you picking your target correctly and you picking your injection site correctly and things like that. So we'll break it all down. The other reason I'm going to break it down is that if you are going to use somebody else's fuzzer, you are going to have to understand all of the pieces that we break it down into, because you're going to have to interact with those for each target, for each way that you inject data in. There will be a different setup regardless of what fuzzer you're using. The target picks how it takes input. The target picks how it gets run. The target picks the best way to be introspected, right? So even if you're going to use AFL, which I suggest you do, and we'll talk about what that is, you still need to understand all of these pieces and how they interact with the target you particularly are looking at the time, okay? So the first time I used a fuzzer, this is before I wrote my own, I was using Spike, which is Dave's fuzzer, and I was looking for exchange bugs. And I was using iCal to do that. So one of the easiest ways that you can fuzz, especially writing your own fuzzer, is file format fuzzing. So file format fuzzing means I take a file that's good, and I make some change to it, and then I have the program loaded up. No problem. It's very easy on all of the steps, right? But to get it into Exchange, I had set up my own Exchange server, so it was going through the Exchange server. And what I did not know is that the Exchange server itself parses all iCal entries so it can put them in its calendar before it ever sends it to the person. So whether or not you open the email, that Exchange server has opened that iCal that your email is going to get. And if it's not well made, then the server gets owned. So I was trying to find a bug in a program that would have been worth like $20,000, and I found like a $150,000 bug in the process. And so that was the first time, and then I was kind of hooked, because basically setting up a fuzzer the first time is a pain in the butt. But once you set it up, you could just run it forever. And eventually money falls out of it, right? And that's a pretty good place to be. So let's talk about kind of how your goals differ depending on what position you are in this chain. So if you are a white hat or you are even a developer, it is your duty to run every public fuzzer there is, right? If you run all the public fuzzers there are against your own code, then nobody in public running all the public fuzzers against your code is going to find any bugs. You're going to find all your bugs first. If you have a developer job and you write unit tests for all of your functions, which you should, and then you set up a fuzzer to run against all of the entry points for those unit tests, you will find every bug that anyone else would possibly find in your code. No one will ever find a crashing bug in your code if you do this, right? And that will be part of the metrics for your GitHub for that job forever. So if you're not doing this, which most companies don't do because it costs time and money and expertise on the part of the users, someone else will, and they'll make it your problem, generally on a Friday afternoon, right? However, if you are a black hat, you also would like to run every public fuzzer, but that doesn't mean you want to use those bugs necessarily, right? If you, as a black hat, find a bug with a public fuzzer, and you start exploiting it, the next person who comes along running that same public fuzzer is going to find your bug, and if it takes you 6 to 8 months to exploit the bug, well, there's a large probability that in those 6 to 8 months, someone else is going to find it. Especially because security research tends to work in kind of a weird child soccer game board, where somebody drops a bug in a particular thing and then it's game on. Everyone looks in that thing, right? Because if you're going after bug bounties and one person finds something in a place no one's ever looked before, there's probably 20 other bugs there. And so if you can jump on it fast enough, you'll get 20K for each of those, and that's that, right? And a lot of people make their living doing that. So one way, if you are a black hat, to use those fuzzers is to say, these are the easy to find bugs in this program. Fix them. Okay, go on to the next stage of harder to find bugs. So you'll have your own patched version of the software, and you'll continue hunting. And you do this at the same time you are doing your reverse engineering and your manual bug hunting, right? So the first step of any bug hunting process is to set up a fuzzer. And I suggest it's probably AFL++ or some other fuzzer that is more advanced like that. Get it set up, get it running, then do the next stage of your work. Because the whole time you're doing the other work, that thing's going to be working for you in the background, finding bugs, right? So while you are doing reverse engineering, and you will be doing reverse engineering regardless, even if you find a bug with a fuzzer, the dumbest fuzzer in the world, you set it up, you run it, bugs fall out, you still need to understand how that program works, to understand, is the bug exploitable? How difficult is it? Would it be reliable? How would this bug be fixed if this is something that I'm interested in doing and fixing the bug, right? So step one, set up that fuzzer. Step two, start to build your knowledge base, okay? And so this is also the process you should use if you are bug hunting for your final project, right? Okay, so each fuzzer is kind of broken up into a bunch of pieces that are responsible for interacting with the program in different ways. And you can build these in more or less complex ways. And if you are building your own fuzzer, what I suggest you do is build the dumbest possible way for each of them, assess the amount of pain that that stupidity causes you, and then prioritize what you work on first to make it better, right? Don't ever build something end to end. Build it modularly, and then assess what parts work and what don't, and then fix the parts that are causing you pain personally as a tool user, right? So let's talk about the input creation and kind of the options that we have there. Okay, so the first way that we can do the input creation for our fuzzer is with mutation, and that's what I talked about with that iCal bug. You take a known good sample, and you have some algorithm modify it. I gave a talk for the Cybersecurity Club on this, and I introduced like a really dumb mutator. And it's what we would call a black box mutator, which means that you don't have to know anything about the format of the file. You don't have to know anything about what the program expects. But what you're going to do is walk one byte at a time through this file. If we think about a file is just a stream of bytes, right? Linear stream of bytes. Here's EOF. Here's offset plus 0. And you've got an index pointer. And at each index pointer, you perform some number of mutations. So one mutation might be, I'm going to overwrite this byte with zeros. One might be, I'm going to overwrite this byte with the max int byte. Okay, I'm going to overwrite this byte with max unsigned int byte. Okay, I'm going to make it an ASCII character. Okay, I'm going to insert at this index a very long ASCII string. So that might be a set of mutations we perform. We perform all of these, we try them, we move the index pointer up one, and we just keep doing that through the file. And you will find a surprising amount of bugs this way, even if you know nothing about the file format. It will take you much longer than if you had done something smarter, but if you don't care how long that computer's running, or if you have 500 computers in a cloud somewhere, it doesn't matter at all. You have to do very little prep work, and you'll still get something out of it, right? So that would be a mutation strategy. And you can do a more intelligent non-black box mutation strategy as well. We could say, well, I know this is a type length data style format where, you know, it's 2 bytes of type and then 4 bytes of length and then some struct. Well, you know, if we know the type list because we have a specification and we know what the structs are, we can say, okay, for every integer in this struct, I'm going to try 0. I'm going to try maxint. I'm going to try 7f. I'm going to try, you know, the sorts of things that I have seen exercise bugs in the past, right? All of the homeworks that you do have values that are legitimate and values that cause the bug to occur, right? If you think about all the ones you have put in that may have caused bugs to occur, those are the sorts of things you're going to want to try in your mutation, right? And so this would be faster because I'm not randomly going through every possible index. I'm saying, okay, I know what to expect, so I'm going to just mutate those things intelligently, right? Because I know how the program is going to parse it. And the further you go down that path, you begin to get into generation, where you say, I have a template for this file format, and I'm going to, regardless of what my input file is, I have no base input file, I will generate arbitrary data that matches the specification, that touches every possible code path, etc., based on this specification or template that I have built for the file. Obviously, you need to know a lot more, and you need to do a lot more preparation, and it's going to be program specific, right? Black box mutation fuzzer, I can throw that at any program without prep. A generation fuzzer is going to take me time to build. So it would be prudent at the start of a project where I'm bug hunting to begin with a mutation fuzzer that knows nothing, start my reverse engineering process, my understanding of these things, write a specification, and then build a generation fuzzer after that, and kind of transition my work. But it doesn't make sense not to run a mutation fuzzer because it's basically free, right? And very often, if you are black hatting or if you're white hatting, speed is the name of the game. If you are black hat, you have a target of opportunity that you've been provided, right? It's only going to last so long. And if you are a white hat, you also have a window of opportunity, which is how long your boss is going to let you work on this thing before it has to be pushed out the door, regardless of whether it's ready or not, which is how life is. Okay? So your efficiency and your speed are paramount in all cases. The final way that you can do this, which is what AFL does and a lot of the more modern fuzzers that are generic that everybody should be using on every single project they ever do, will use some sort of feedback loop, which means they will use either something like a pin tool that does code cache modification, or they'll recompile the binary with introspection in it so that they can monitor code paths and say, okay, this time I took this branch and I haven't taken this branch yet. So I'll use a genetic algorithm or a SAT solver to say, if I'm in this situation, what kind of input would make me take the other branch? Okay, now I've generated a new input. And based on that, they'll try to do full code coverage for the whole program. Now, code coverage is not the same as all code paths, right? Especially if you are looking at object-oriented code and vtables and looping. There are many different ways that you can reach every code position. So this is not foolproof, but there are some pretty good ways to do it that people have provided. Now, if you go and look at AFL, which we'll talk about at the end of this, Michael Zalewski, who wrote it at Google, is no longer writing it. There's now a new version that's community developed, AFL++. But he has a document in the root of his GitHub that explains why he made a bunch of choices and how it's built. And it is extremely opaque, because it is like a magic trick in that the answer to a magic trick is the dirtiest garbage you've ever seen in your life. That's why you can't guess how a magic trick works. It's not elegant, it's garbage. And so for every problem that he saw in his fuzzers over time, he has come up with kind of a halfway dirty solution that splits the difference for most programs. And so reading that document is a list of dirty solutions to problems you don't understand. And until you write your own fuzzer and kind of are familiar with how each of these problems affect it, those solutions are not going to make sense, right? And so that's the sort of thing you get into with advanced fuzzer creation. Luckily, the code is all out there, so you should be using it. Okay, so we've got some input. And our next problem is, how are we going to run the program? And this is going to be based on the program. The programs that you've looked at in your homework are all command line utilities that take arguments from the command line. So all the data is input as arguments on the command line. That is not how software generally works. Sometimes people need to click on stuff. Sometimes it's a network service. Sometimes the service is run manually. Sometimes the service is run by a service monitor that will restart the service if it crashes. Right? All of these things matter. And then further, your operating system is going to say, have a say about how you can monitor that process. So the easiest way on Linux to do this is to let something crash and build up crash dumps, right? But if you have a system that's got some post-mortem debugging set up, that's worth using. If you have a system where you can run the service inside a debugger, that's even better. All of these things will change based on what software you're looking at and how that software itself is interacting with the system. And so this is one of the problems you're going to deal with even if you're just running a fuzzer, right? Once we've got the sucker running, we've got to get the data in. As I mentioned, there are all different ways to do this. Now, the first way that you're going to think of is the way that the data is supposed to get into the program, right? But imagine we are fuzzing a service, and it's making use of a library, and we are pretty sure most of the work gets done in this library. It may behoove us to load the library up with our own custom harness, and then call the functions of the library, knowing what all the types are. So if I've got to deal with a network server, I've got to write a network protocol myself, and then I can fuzz that network protocol on the way in. But if I'm calling a library and I know the types on the function calls in the library, I can wrap that library, load it up myself, and just call the function calls directly and do generation fuzzing on the simple C types that it's taking. Does that make sense? Yeah, and it's a lot faster. You could even go a little step further and run a program to a certain point and snapshot it in QEMU or VMware or Hyper-V or whatever you're using for virtualization, and use a debugger script to inject data in or make changes to memory, and then run it, and then revert back to the snapshot and make a different change to a memory page and run it again. And a bit of that strategy is what AFL is going to do for you to figure out how to do its code coverage. But all of these things are entirely feasible. This is the most obvious and often slower way to do it. Actually injecting it directly in with a library call is simple and faster, and then more complicated but faster still and even more powerful would be making modifications in memory. So let's take an example like, we'll take a simple example that we looked at before. Let's do ABO1. You know what your stack looks like. You've got argv and argc, and you've got old EBP, and you got ret, and you got buff. And buff lives here, and buff moves around generally. But if we snapshot at the start of the program, buff does not move around, right? Oops, I'm getting it wrong. So let's imagine in order to get to the point where stir copy gets called in ABO1, it actually takes 20 seconds every time we run it, right? But it takes us 2 seconds to reload a snapshot of the program. When we take that snapshot, we know exactly where buff is in memory. We can look at that. It's not going to change once we snapshotted it because we're not restarting the program. Okay? We're just going to come back to that state. You can just manually change this data. I have not mentioned this yet, but even in GDB, you can just edit bytes of memory and edit registers on the fly to whatever you like. Every debugger will allow you to change memory however you like, right? So you can revert back, have a script in your debugger that makes this some arbitrary value, and then try it again. And so in that case, you'd save 18 seconds per run. And since you're going to run 500,000 times all night long, you're going to save, someone do some math. Don't bother, a lot of time, right? The more cases that you can get in, the higher your odds are of getting bugs, right? So this is a very dumb example because this program is extremely short, but if it were a larger program, or perhaps it included like a login timeout or some sort of thresholding for how much data it takes, this would solve that problem, right? Does that make sense? So a little bit more advanced, but if you sit down and try it, you will find you are entirely capable of making it happen, right? You're probably going to crash it a few times figuring out how to do it, but it's actually very simple if you understand where the data is. If you've got something like a program that reads from a file, it'll be way faster to do it that way than to write a file to disk, run the program, load the file, do it. That's an easy fuzzer to write, and probably the one you should start with, but eventually if you want to make it fast, that's the way to make it fast. Okay. So the next step that we've got here is going to be our process monitoring. Our goal here is to make the program crash. How do we know when it's crashed? You might have another goal, which is put the program in a particular state, which would be a little bit more complicated to figure out. A crash is a specific version of that that's easy to find. So how do we do that? Generally, you've got a debugger harness that you're going to be running the program in. If you don't have that, these are the dumbest two ways to do it. On Linux, a crash dump will be created. It will be dumped into a file, right? And you can monitor that directory to say, hey, did something crash or not? Okay. On Windows, you've got post-mortem debugging. So normally on Windows, something crashes, you get a little pop-up that says, can I send this to Microsoft? Or you used to, probably now it just sends it to them without asking. Anybody remember Dr. Watson? Yeah, Dr. Watson is the default post-mortem debugger on Windows. But you can set up literally any program to run as your default post-mortem debugger. It is a registry key. You can change it so that when a program on your computer crashes, any arbitrary program is run with arbitrary arguments. If you have WinDebug on your Windows machine, and as admin you type WinDebug/I, it will log WinDebug as your default postmortem debugger. And anytime something crashes, you'll get a straight-up debugger window that's interactive on that process before it goes away. So you can, and I suggest if you're running Windows that you do that, so that you can see how often things silently crash on your computer and what software is reliable and what software isn't. Because currently it's hiding from you when it crashes, right? But you would be able to see, oh, hey, look, I found a free bug. And sometimes that happens. I've definitely found free bugs just having a postmortem debugger set up on my computer. Something crashes randomly, you look at the registers, you look at what was just executed, and you're like, oh, yeah, look, that's writing what looks like controllable data to a memory address that doesn't exist. That's great. Right, free bug. These are the cheap ways to do it, but they are not particularly efficient in the long run. What you will find, and I'll tell you a little story, is that the problem is not finding bugs. The problem is dealing with the hundreds of thousands of crashes that you have on hand. So a while ago at CanSec West, a guy named Charlie Miller gave a talk where he had written, the point of the talk was to show how bad software was, basically. And he had written a mutation input generator, and all it did is pick a random offset in the file, or a random number of random offsets in the file, and randomize the byte that was there. That was the extent of this mutation program. And then he ran it through 30 to 50 very common programs like Adobe Acrobat and web browsers and all sorts of other lovely things. And they provided him hundreds of thousands of crashes. And he was like, look, I found all these exploitable bugs in this stuff with this stupid, stupid fuzzer. Now the trick is that he showed you the dumbest part of his problem. The hardest part of his problem was, I've got hundreds of thousands of arbitrary crashes on my computer now. How do I sort those, figure out which ones are the same, exercising the same bug, which ones are unique, and then which ones are worth putting time in to write an exploit for, or even prove that they're exploitable to get them fixed by a vendor. Even if your goal is to get bugs fixed by a vendor, you still need to do the triage. They're not going to be happy if you're like, here's 500,000 random crashes, they'll never fix them, right? And your goal, if you're doing that, is probably to be able to write up something and get it on your resume. So you could say, found 200,000 crashes in this program. And you can't really do that, well, you can, but the company that you're talking to will be upset with you if you just dump it out there. So there's an optics thing that you have to make a call on, right? But they're not going to want you to say anything about it until they've fixed all of them. And triaging that is going to take them forever. So you want to triage first, especially if you're trying to get bug bounties. Or even if you are working for a company and you are trying to help someone write better code, you still want to triage it for them, right? Those developers are busy, and their deadlines are too short, and their teams are too small, and the reason they didn't find those bugs in the first place is those reasons. So you dumping extra stuff on their head is not going to make the situation better. They will be more stressed out and write more bugs later on. So that was what he hid from everybody. And the way that you solve that problem is by process monitoring intelligently. So running your program, your target, inside a scripted debugger of some kind, making a decision about what data is necessary for you to figure out if a bug is the same as another bug, or if that bug is likely to be exploitable. So for me, I take a number of things into account when I'm doing this. In a second, I'll talk about storage and what to store. Next. Yeah, there we go. So Normally, when something crashes, what people will give you is a backtrace. All of the time. And it is almost entirely useless to making a smart decision about what's going on in a bug. That is, how did we get there, right? It's not what went wrong. So what would you look at to know what went wrong? When you are looking at your homeworks and something crashes, what's the first thing you do in the debugger?
Wait. Check.
Well, you already got a breakpoint, right? Because when it crashed, it breaks for you. So what do we look at?
Backtrace. Wait, is that
Throw him out. He's been demoted.
EIP?
Yeah, okay, so EIP is the first one.
Back for what EIP is reading.
What EIP is reading? What instruction just ran? Something faulted. It was the last instruction that ran. What instruction was it, and why did it fault? Right? Odds are, probably it read from or wrote to a bad memory address. So I want to know two things. I want to see that instruction. I want to see a couple instructions before that to know how it got there, where it got that data from, theoretically. A couple instructions past that to see what it's going to do with that data. Right? So before will tell me, where did you get that bad address from? Instructions after will tell me, what are you going to do with the data that you got from that bad address? Right? So first one is, did I send you that data? Do I control that data? And then the second one is what if I do control it and I point it at someplace intelligent, what are you going to do with it next? Are you going to treat it like a function pointer? Are you going to write something to that address again? Right? All those things are important to know when we're assessing exploitability. The last thing I'm going to want to look at is probably the registers. Right? Because if it says move, okay, I look at the instructions, it says move ECX, EAX. Do I control EAX? I don't know. But if I look at EAX and it turns out that EAX is 62, 41, 43, 70, well, that's probably ASCII, which means it's probably something that came from input from a user, and then that's definitely great. Great news for me, right? So your scriptable debugger on crash should pull that information, and you should put it into a database. If you put it into a database, then you can look for matches in the database, right? Like you could unique it and say, okay, now bucket everything that looks exactly the same, or same crash and same backtrace together is probably going to be likely a similar crash, right? You could figure out an intelligent way to hash those things together and come up with an even faster match. The other thing that you could do is say, oh man, the last bug I found in this program that I sold looked like this. Show me all the other crashes that look exactly like that one that they have not yet patched. Did I find another path to the same bug they didn't cut off? Did I find another pattern that looks exactly the same that somebody copied and pasted elsewhere? All those things are possible, right? Because it's the same developers copying code from each other over and over and over again. And so I want to be able to make those distinctions as fast as possible. The best way to do that is to get that information, put it inside a database, and work with it there. That's a little bit of work. So what do you do if you deal with something on a dumber fuzzer? Say you made a fuzzer like the one that I went through in the Cybersecurity Club, which I will drop the recording of later on so you can go through that. In that case, what they were doing is letting the program dump core and then just looking through the core dumps manual, right? It's not much work to build that thing, but here's the problem. What you probably want to do is even script up your crash dump analysis to do something like, if a crash dump hits that directory, script up a GDB that dumps out that data I just mentioned into a text file or something else, and then delete the crash dump. Because if you don't do that, you're going to fill up Larry's laptop and it won't boot anymore. You should also remove all of your test samples that didn't crash. You keep the ones that crash stuff, but immediately upon recognizing that a certain input is not useful, delete it, or you'll fill up Larry's laptop and you won't be able to boot it anymore. Which is what happens. Right? So keep those things in mind.
Are there any tools for going through and doing that, like putting the various crashes into buckets? Because like we have one that I use at work that I really like, but I haven't been able to find anything like it.
So WinDebug actually has built-in a plugin called Bang Exploitable. It's like exclamation point exploitable, and it'll hash that thing up, and it actually kind of takes a guess whether or not it's exploitable. I don't know if it's still maintained. It was pretty old last time I looked at it, but no, there is no...
I don't even mean for finding out if it's exploitable, but just taking various crashes and putting them into like kind of like buckets. That way, you like investigate the bucket as a whole.
No, that's the trick that Charlie Miller didn't discuss, right? And if you hadn't been in the position before, you would not recognize that he did not discuss the hard part of the problem. And I suggest if you do talks at conferences that you obscure the hard parts of your problem so that other people can't steal your research. I thought he was a jerk at the time, but now I'm like, oh man, this is a smart guy. So each of those pieces that I just showed you, if you are building them one at a time for specific projects, keep them. It would be very smart, instead of building one monolithic piece, to modularize yourself a Fuzzer framework that you add to as you go, right? And each of the pieces, each one of those pieces that we talked about, can be mixed and matched for different targets. And so if you are going after file format bugs for a while, so bugs like that iCal bug or bugs in PDFs or things like that that require that kind of injection, don't rewrite that injector later on, save it off, right? If you have it intrinsically tied to the framework itself, you will not be able to reuse it if something else changes. But if you break up your development into those pieces that we just talked about, all those pieces are reusable, and you will have them in your pocket later on. So you write it once when you're 20, and when you're 30, you've got it. When you're 40, you've got it. When you're 45, you rewrite the whole thing because none of the libraries work anymore. But you'll have done it before, and so it won't be that bad, right? You can also integrate other people's entire fuzzers into pieces of your modularization if you do it well, right? So you could be running someone else's generator and someone else's injector, but still be pulling out all of the data that you want into your database for the way that you work, and be able to cross-reference it with other types of fuzz projects that you have, right? So this goes for basically all of the code that you write. It's very easy when you start, even if you start doing like CTF type stuff, you will find that you write the same boilerplate code over and over again. That's what became PwnTools, is somebody's boilerplate code. But you are going to write your own boilerplate code, right? And it's going to be the way that your brain works. And so build your own libraries and save your own code off and make your life easier and work in the same way every time that you work. And you'll see that a lot of professionals do that. And one of the downsides of that is that sometimes if you've looked at just a whole slew of exploits, you can say, ah, a Russian wrote that. Oh, somebody from Mantech wrote that. Somebody that was at Mantech in the 2000s wrote that because of the term that they used there, right? Those are the sorts of things that you'll start to recognize because this is the efficient way to do stuff. And I think the people who are doing that kind of work are doing a lot of that stuff when they are doing attribution nowadays, right? Like that's how that attribution takes place, is we see the same problems in exploitation over and over again, just like you see the same problems in development over and over again, right? Every computer is built out of linked lists and arrays of structures. That's just how it is, because that's how the architecture is and that's how math works. And so when you're doing exploitation, you're exploiting those structures, you have the same problems, you will come up with the same solution or similar solutions, but yours are different based on your the way that you learn, right? So if you guys go out now and you start writing exploits, somebody will say, those people never return to an address that is unreliable. They are always returning to libraries. Probably they are from this lineage that runs through me, from some people at Mantech, from the Argentinians, from blah, 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 right? It is a style. Some of the terminology that I use in this class is of a lineage that other people don't use. So when you use it, you will be marked by the lineage. All right, so what is AFL? It's American Fuzzy Lop, which honestly, furry trash runs deep in this space. But it's the name of a fuzzer that Michael Zalewski wrote right before he came to Google, and then subsequently later while he was at Google, until Google stopped funding it. And then it became a public project, AFL++. It is doing a lot of nasty stuff in the background for code coverage. Now, this is not code path coverage, but it is code coverage. It will be able to say, I have touched every basic block that this program has run, or 70% of these basic blocks. And so when I say basic block, if you looked at Ghidra or IDA's output, where it shows you each branch as being connected to a separate block, or if you've done the grad homework, it will be able to color those, right? And it is doing this using introspection. So there's two ways. The first way is, if it's an open source project, you recompile it with an AFL compiler that places coloring code at the beginning of each block. If you are looking at binaries, which it can also handle, it's going to use something like PinTool, which is a code cache tool. For a while, Pin was huge right when it came out. I have not found quite so many uses for it because it is extremely slow. But what it does is, it will load a binary up, and then it will instrument it in the code cache. So the binary that's being run doesn't change at all, but what happens does change. And so you could provide callbacks in real time that are very quick. So imagine you have instrumented a binary with a bunch of breakpoints in GDB. So at each basic block, I set a breakpoint, right? And I could write a script for those so that when that break occurs, I print something to a file. And then I could do code coverage like that. The problem is it's very slow, because every time you hit that break, there's a context swap. It goes to the kernel says GDB handle it, GDB runs the script, it says continue, it goes back to the kernel, it goes back to the process. What Pin lets you do is there is no context switching as you're going, right? The instructions for instrumentation are just part of the code as it runs, and you are always in context of that process. Okay. The way that it is figuring out how to do its code coverage is the same way that a SAT solver will do it. Okay. So is anybody familiar with SAT solvers or SMT? Yeah, or concolic execution style stuff? That's basically what's happening there, okay? You are essentially building a truth table. You ever do one of those word puzzles where it's like, somebody shot the baker and the person who shot the baker was wearing a hat, but Teamsters never wear hats, and Julie is a Teamster and she's sleeping with Bob, and Bob drives a red car, and now figure out who killed the baker. You build an enormous truth table for that, right? And you can very quickly cut off huge chunks of that truth table to solve that problem. And that's basically what your SAT solver is doing. It is all just binary logic, right? It's the same way if you look at my SAT solver for ARM, which is on my GitHub, every register is mapped as a bit vector of 32 bits, and they just are true false. And so the entirety of a program and every instruction gets cut down into what happens to the truth table of that register when this instruction is run, right? And so the SAT solver can say, well, if these 4 instructions run, then my truth table, in order to get to this state, it only can be this piece of the truth table could have 1. So now I'll try a random piece in there. I'll try something random within that truth table as a value. and I'll see if it works, and if not, I'll try a different one, right? And that's basically what AFL is doing in the background. You might hear people call that a genetic algorithm, where you are trying something, looking at what happened, and then mutating hotter and colder based on that, but that truth table is basically how it gets done. This is a very advanced fuzzer that was written professionally by someone who has been an excellent bug hunter and a good mathematician for many decades when he wrote it. There is no reason not to run this thing if you have the opportunity to. If you are writing your own code, you should run it against it so that no one else finds bugs in your code. If you are hunting on a project, the first thing you should do would be have your intern get that running on it. Like that's like the first thing. You take the least experienced person on the team and you're like, go set up this target and make AFL run it and then come back and talk to me again, right? If you are working alone, that's your first step. Your second step is start to learn about the target. But before you even learn about it, set that thing up and let it run, because it'll do a lot of free work for you, okay? Ooh. Really today, let's talk about, in our last couple minutes, homework 2, which is not up yet, but will be up.
It's up.
It's up, okay. So homework 2 is a binary. There is no source code provided at all. Okay? Your first job is going to be to reverse engineer that binary. And you're going to reverse engineer it in a particular way. I do not want simply basic blocks. How am I defining basic blocks? If I have a branch, I've got to know. I even have a green marker. This is perfect.
It's great at
And I've got a yes. I don't have a black though, unfortunately. Both of these come to a final block, right? This is just based on a branch, so a jump not equal or something similar to that. What I actually want you to do is break this sucker down into logical thoughts that you would have as a programmer if you were writing this program. That means that each of these blocks might have 2 or 3 lines of code in them, in C, right? I want you to break down the program into that level. If you are writing this program in C, how are you thinking about it, okay? Not just, is there a branch, true, false, but like inside each of those blocks, if you call a function and there are arguments to that function, that's one thought, right? Like stir copy, dest, source is a single thought. So break it down into that, okay? Your job is to write a report on the thing so that someone who can't read assembly understands what's going on. So if you write up descriptions and they rely upon somebody understanding assembly, it's not going to be good enough, okay? That's step 1. Step 2 is going to be, you are going to write the C code that when compiled with the makefile that I give you is also ownable by the same exploit that owns the original. That means your stack's got to be the same. It means the local variables have got to be the same, right? If, when you recompile it, gadgets is in a different spot, so that doesn't work, that's fine. But your exploit should get EIP on your compiled version of your source. What's the last part in there? Oh yeah. You're going to write your own shellcode. That's the last piece. In assembly. And that shellcode is going to read a flag off of the drive and print it out. And that flag is going to be of an arbitrary length, which means what you are not going to do is make yourself 200 bytes of space and then read the flag into it, or read 200 bytes out of the flag. You're going to have a read loop that looks at the value returned by read and keeps reading until it gets onto file. Cool? There is going to be no extra grad student homework this time. And the reason is because I would like the grad students to be churning on their final project now. And so that means when we talk on Thursdays, we are going to sit down together and talk about what you've done, where you're stuck, what you understand and what you don't understand, and what your process is for prosecuting whatever your final project is. And I will walk you through that process, but we're going to start that sooner rather than later, as I have found there is a propensity for procrastination amongst certain. And that would be a mistake. So we're going to do what we can to prevent that. Does anybody have any questions about process stuff or midterm stuff or homework 2 or homework 1? What's the due date on homework 2?
2 weeks, right?
I think it's after 2.5 weeks, sometime after spring break.
I think it's the day that spring break ends.
Yeah.
It's the 25th.
Oh, me. Sorry about that. I don't. When I wrote the syllabus, I basically used the syllabus for the last time it was taught because I was told I had to, because in time we couldn't get it through the panels fast enough for me to change stuff. So I used the dates.
So Steven hates us.
Steven hates you retroactively. Yeah. That's basically what happened.
It's not a hard homework. It's pretty easy.
Homework 2?
Yeah. It's easier than one of my.
Yeah, it depends if you find the bug easily or not. The bug's a little bit more subtle. We have already discussed this type of bug in class. So if you go back to the lecture on bug types, it's in there. And it's not that complicated an exploit once you find that bug. The complication here is you doing the reversing, you understanding it, you writing the C, and then the shell code will be a pain. I suggest you write that shell code in NASM and then bring it over into your Python. If you want to use any tools, what's on the grade scope? Is Punctuals on there?
Yeah, Punctual's on there. I don't know how well it works, but.
All right, well, you're taking your life in your hands if you use Punctuals to do it, but I will not stop you.
You just have Punctuals like print the exploit and make a new Python file that.
Yeah, that would work fine too. You could write another script that uses Punctuals to write it. NASM is generally easier. Here's the thing. If you bug the fuzz, which is Jade, she's also the grader. So don't bug the fuzz. Make it easy for Jade. Don't make it hard. All right. Anybody have any other questions for today?
Oh, if you need last minute help with the homework too, I'll help you in office hours later.
Kids having office hours after the original due date of the homework, which is extremely generous.
Yeah.
Extremely generous.
We fixed it. Wait, was this supposed to be due?
It's supposed to be due at midnight last night.
Yeah, last night.
We'll see if somebody still needs help.
We added an extra day specifically to torture you.
I don't mind. I would love to have office hours.
When I came into class, there was 46 entries in the code, I think.
And we're pretty good on code. Surprisingly, mostly caught up. I think we have a few left, and many of them are
Close to 60?
Yeah.
Okay, cool. Excellent. But yeah, I'll stick around a little bit to answer questions about questions too, because some of it is not entirely straightforward.
Will you be helping with the two during office hours?
Homework 2? I have not done it yet. I think I understand the concept.
Isn't showing the office.
No, stop. No, you can't let people know about the
John, what do you mean? Victor does it great. Why is that goal?
The next
No, I don't
Thursday is about
no disassemblers. No disassemblers.
So,
Oh, I know.
right now-
Sorry, no disassemblers.
Oh wait, yeah. I got the picture.
So,
Yeah.
Homework's okay. It's like you have time.
Man, this chicken come here.
I had the picture.
I think I got
That's like.
I gotta go to.
You can't write the values to the query because there's nulls in there, spaces.
Are you still like watching your
Those are for not so remote, like actually right?
Yeah.
I can do reps. I know it. I did not see the.
Getting out again.
You writing in there now.
If you're able to read it. Check your own attendance. Check your own attendance.
What happens when you write opposite?
I think it's now.
Technically, now the index is pointing at 41, 41, 41.
Yeah, it's
The next thing you need to right drive pointer across 41, 41.
Yeah, it's gonna be later. So check. We have a Google Calendar. I don't know if you know about that. Check the Google Calendar for when exactly. No, it's in the shower. The highways.
Think about how not overwrite the theory, but overwrite red.
Yeah, I'll mark it right now.
Well, I'm with Brody. Oh, wait, I'm with Joseph.
Should I end it with like
What is I stand for?
why is this the end?
Hold on. You guys say, immediately check it.
Should it not be just right after your chunk finishes? Or like
Whatever you set it to is where the next page will be written by the index. Write something else. And they're all written. Like things that we want. I think just two things.
yeah, just
Jade actually has all this stuff.
Bigger scale. It's gonna be like half like you know like you each player.
So this is the online one.
Yeah, we're still gonna have like we're still gonna like attack on you. So we're like asking you to like get like some
So it is April 18th to 22nd, whichever the midpoint, April 18th, I think. So we're thinking, so it's over a weekend in April. Yeah, so like probably talk with me on Friday, it's up to you. And then basically it would be like an international audience, so you can go for like a really, if you want to do a hybrid, you can do it just for UMass students, or you can do a hybrid talk. If you do a hybrid talk, it would be for like a pretty technical So if you're interested, if you don't have time, that's like fine, but like if you're interested in giving like a talk.
Yeah, I mean, I could pre-write one of the later classes for this class and give that talk. Yeah, I'll find something. Send me a message that has information and I'll send you a couple talks.
Do you have a time preference for Friday, Saturday, Sunday?
Send me the dates and we'll discuss it on Discord when I can work on my schedule.
Yeah, that's fair. And then, are you okay with it being hybrid? Yeah. So live streamed and also like indoor. Sounds good. Second thing was just about the semester project stuff. So we're basically cleared on finding something. I guess we'll talk to Andrew and Galen and Dunod, and we'll get you guys back. I mean, for this class or for the club project? Yeah, sounds good.
Let me know when we want to do that and I'll get Ryan to come in.
Yeah, we were thinking of a smart block. I think that's what we've been throwing around. Okay. But do you have like any ideas for targets? Because we really don't know yet. We're thinking maybe a smart block.
Select something. And go after it if there is. That's what I would do. Just because that'll make sense.
There's old printers in the basement of the Hilger that I think are left for scrap, so we might be able to steal one of them.
Is it in the pile that says not protect disposal?
No, it's the one outside the E-Lab.
Okay, yeah, I got you.
Not the E-Lab, the engineering shop. But yeah, alright, thanks for
Oh, yeah, would you like a cookie? Brown butter, chocolate chip.
If I static the college,
That's nice. I have a reference of homework for
you saw these already.
Yeah, I did see that.
They're eating glass.
I'm thinking it's not.
I was